The universe might be hiding an entirely new force of nature, simply because we have not looked closely enough at the heaviest and most unstable particles in existence. How can a single particle that vanishes in less than a trillionth of a second prove that our entire map of the subatomic world is incomplete? In this video, we will answer that exact question by looking at the latest results from the Large Hadron Collider at the European Organization for Nuclear Research. You will understand how the tau lepton is putting the most fundamental rule of particle physics under extreme pressure, and why the latest measurements have narrowed the search for new physics to a razor-thin margin. The core mystery we are investigating is the concept of lepton universality, which is the idea that nature treats different families of particles with total equality. According to the Standard Model, the electron, the muon, and the tau lepton are supposed to be identical in every way except for their mass. If we find that the tau lepton interacts with forces differently than its lighter cousins, it would mean that the Standard Model is wrong, and a new force carrier must exist. We know that electrons are stable and easy to track, while taus are so heavy and short-lived that they leave almost no trace. One small payoff to understand right now is that the tau lepton is 3,500 times heavier than the electron, making it the perfect probe for hidden mechanisms that only appear at high energies. You can see this reality in the way detectors have to work backward from a spray of debris to even prove a tau was there in the first place. The default story that physicists have relied on for decades is that the three generations of leptons are simply copies of one another. This rule of flavor blindness means that if you swap an electron for a muon or a tau in a decay process, the physics of the weak nuclear force should not change. This is a very clean and beautiful symmetry that has passed almost every test for 50 years. However, scientists started to notice strange signals in the data from the Large Hadron Collider Beauty experiment several years ago. These signals suggested that certain heavy particles, called B mesons, were decaying into electrons more often than they were decaying into muons. This was a massive contradiction, because the theory says the rates should be almost exactly equal. These contradictions were often dismissed as statistical flukes, because the decay processes are incredibly rare, occurring less than once in every million events. When you are dealing with such small numbers, a few extra detections can look like a revolution when they are actually just random noise. To solve this, researchers have turned their attention to the tau lepton, the heaviest sibling in the lepton family. The logic is that if there is a new force, or a hidden particle like a leptoquark, it would likely show its strongest effects on the heaviest particles. The first major anchor of contradiction comes from the sheer mass of the tau, which allows it to decay into hadrons, something electrons and muons can never do. This creates a messy signal that is very hard for the detectors to distinguish from common background noise. In the Standard Model, the calculation for how often a B meson should turn into a pair of tau leptons is extremely precise. If the actual measurement at the Large Hadron Collider shows even a slight deviation from this number, the old model fails. This brings us to the first insight loop regarding the difficulty of measurement and the precision of the current limits. Scientists at the European Organization for Nuclear Research recently set the most stringent limits in the world on how often these rare decays happen. The old model predicts a very specific and tiny rate for these events. The contradiction lies in the fact that, while we have not seen a clear excess yet, the window for where new physics can hide is shrinking every day. This matters because it forces us to refine our instruments and our software to a degree that was previously thought to be impossible. By narrowing these limits, we are effectively cornering the universe and forcing it to reveal if the lepton rule is truly universal or just an approximation. To understand why this is so difficult, we have to look at the flight distance of a tau lepton. A tau only travels about 0.1 millimeters before it decays into other particles. This is a distance smaller than the width of a human hair. The Large Hadron Collider detectors must use microscopic vertex precision to find the exact point where the tau was born and where it died. If the detector is off by even a tiny fraction, the entire event is lost or misidentified as a common quark. This is the mechanism of reconstruction, where physicists act like forensic investigators at a crime scene where the body has already been dissolved. They have to use the trajectory of the visible fragments to calculate the point of origin. This changes our understanding because it shows that the limit of our knowledge is not just the power of the collider, but the precision of our spatial measurements. Each time we improve this reconstruction, we are testing the standard model with a higher resolution than ever before. Another massive challenge is the missing energy problem caused by neutrinos. Every single time a tau lepton decays, it produces at least one neutrino, which is a particle that can pass through solid lead for light years without stopping. This means the neutrino carries away a large chunk of the energy and momentum from the decay, and the detector never sees it. This creates a permanent hole in the data that makes it impossible to fully reconstruct the mass of the starting particle. Physicists have to use complex conservation laws to guess what the neutrino took away. This is a fundamental limit of the instrument. If the old model is true, the missing energy should follow a specific statistical distribution. If we see a shift in that distribution, it suggests that something else was created in that decay that we did not account for. This pushes the emotion of reverence because it highlights the extreme lengths humans go to in order to measure the invisible. The recent work on rare transitions involving two tau leptons is the most difficult test yet. These events are so rare that they are like finding a specific grain of sand on a vast beach. The Large Hadron Collider Beauty experiment has been upgraded with a new software trigger that can analyze these events in real time. In the past, the data was so overwhelming that the computers would simply delete these rare events because they could not process them fast enough. Now, we are rescuing these taus from the digital trash bin. This technological leap is what allows us to push the pressure on the lepton rule. It changes the game from a search for a needle in a haystack to a systematic sorting of the entire stack. This is a shift from luck to pure engineering and data science. One of the most interesting competing models for why the tau might be different involves a hypothetical particle called a leptoquark. These are particles that would carry both the properties of quarks and the properties of leptons, acting as a bridge between the two main families of matter. If leptoquarks exist, they would interact more strongly with the third generation of particles, which includes the tau lepton and the beauty quark. This would explain why we see potential hints of trouble in B meson decays, but not in everyday electronics. The measurement method here involves looking for a specific pattern of decay that only a leptoquark could produce. By setting the world's most stringent limits, the team at the European Organization for Nuclear Research is effectively saying that if leptoquarks exist, they must be much heavier or much rarer than we originally thought. This tightens the leash on theoretical physics and forces us to reconsider the scale of the universe's hidden machinery. We also have to consider the role of the Z prime boson, another potential new force carrier. While the standard Z boson is well understood, a Z prime would be a heavier version that might only talk to certain types of particles. This would break the rule of flavor blindness and prove that the fundamental forces are not as simple as we once believed. The proof for this would be a slight preference for taus over muons in specific high-energy collisions. Currently, the data shows that the standard model is incredibly resilient, but the pressure is mounting as we collect more data in the third run of the Large Hadron Collider. The sheer volume of data being produced now is a flood compared to the trickle of previous years. This matters because many of the early hints of new physics were just statistical fluctuations that vanished when more data was added. This teaches us the importance of patience and the unforgiving nature of the scientific method. There is also the problem of fake signals, where common jets of quarks look almost identical to the signature of a tau lepton. To find one real tau, the scientists have to reject 99.9% of the events that the detector records. This is done using advanced machine learning algorithms that are trained to recognize the subtle differences in how a tau decays versus how a quark jet spreads out. This is a hidden mechanism of the research that most people never see. It is not just about smashing atoms together. It is about building an artificial intelligence that can see patterns in the chaos of subatomic debris. This increases the stakes because it means our discovery of new physics is now tied to our ability to write better code and train better models. If our algorithms are biased, we might miss the very signal we are looking for. The idea of the three-prong handle is another crucial tool in this forensic investigation. When a tau decays, it often produces three charged pions, which leave three distinct tracks in the detector. If you have two taus decaying this way, you get a very specific geometric signature of two vertices, each with three prongs. This is much easier to identify than a single track. This measurement logic allows researchers to filter out the noise and focus on the most promising events. It is a reality check on the data. If we do not see these three-prong patterns at the expected rate, we know our understanding of the background is flawed. This level of detail is what makes the current research so powerful. We are no longer just looking for big explosions. We are looking for the geometric alignment of invisible paths. Why do most people not know about this hidden tension in the tau lepton data? It is largely because the results are often presented as limits rather than discoveries. In the world of science, a limit is a statement that says we have looked in this specific area and found nothing, which actually narrows down where the truth must be. It is a process of elimination that is less flashy than a new particle discovery, but just as important. There are also incentives in the scientific community to focus on the most certain results, while these rare tau decays are right on the edge of what is possible to measure. This is a gap in the public understanding of how science actually progresses. It is a slow and steady closing of doors until only one path remains. This process of elimination is what is currently happening with the lepton universality rule. We are systematically checking every single way the rule could be broken. Now, we must address the question of the title and provide the verdict that the evidence demands. How does the tau lepton answer the question of whether the lepton rule is broken? The direct answer is that while the evidence has not yet shattered the standard model, it has eliminated the most obvious and simple versions of new physics. The measurements have proven that If there is a violation of lepton universality, it is much more subtle than the early anomalies suggested. The evidence eliminates the possibility of large, easily visible leptoquarks at low energy scales. However, the result still has no account for the persistent small tensions that refuse to go away as the data grows. The mechanism that remains strongest is that the standard model is an almost perfect description. But it likely sits inside a larger, more complex framework that we can only see through the rarest of decays. The interpretation stays open because we are still waiting for the full data set from the current high-energy run to provide the final statistical weight. What this changes for you is the realization that we are living in a moment where the most successful theory in history is being pushed to its absolute breaking point. The tau lepton is the weight that is being used to test that bridge. If the bridge holds, we have a deeper appreciation for the standard model. If it breaks, we are standing on the threshold of a new era in human knowledge. The forensic intrigue of these tiny, invisible traces is the only way we have to look behind the curtain of reality. We are looking at the smallest things to understand the biggest rules of the cosmos. As we continue to sift through the billions of collisions happening every second at the Large Hadron Collider, we are not just looking for particles. We are looking for the cracks in the foundation of the universe. The clarity we gain from each new measurement brings us one step closer to knowing if we are truly alone in our understanding of the forces that hold us together. If you want to stay at the frontier of these discoveries, as the data from the third run continues to pour in, make sure to follow the updates from the European Organization for Nuclear Research and the teams working on the Large Hadron Collider Beauty experiment. The next few years will decide whether the lepton rule stands for another century or falls to the pressure of the heavy tau.